Hello, my name is Richard Danz, and welcome to my presentation, Surfing on a String. So, what does Nick Wallenda, a famous high-wire artist, and an acoustic guitar have in common? Well, it's string. Think about it. A tightrope is made out of string, and so are the strings on a guitar. So, what is the value of gravity resulting from changing the tension on a string in harmonic motion? This will be explored to help relate to those two topics. In order to fully understand the physics behind this investigation, we have to discuss what harmonics are. So, in relation to this investigation, a node is a point where there's destructive interference in a wave. That is a point where the wave kind of cancels it out when it bounces back to the original wave. That is signified by the red dot. And the opposite of that is an antinode, which is a point in which constructive interference happens and the wave becomes maximally amplified. And a point where these two antinodes will oscillate between 2 points is called a loop. And the number of loops in a wave is what determines the harmonic. For this experiment, a wave in its second harmonic will be used, as shown in this figure 1. It's not really shown here, but the loop is kind of like where I'm outlining right now. So how does gravity relate to a string in harmonic motion? Through a combination of 6 equations, gravity can be related to a string. The first equation has to do with wavelength. Second one is linear mass density, which applies to the string. The third one is just the equation for tension. Equation 4 is velocity of a wave traveling through a medium. Equation 5 is the velocity just being related to frequency. And then equation 6 brings back all of the previous problems and relates it to tension. And then equation 7 isolates gravity. Some of the variables are listed on the below, and those will just be used in calculations. So design and materials. Figure 2 shows what the experiment looked like with, in this top left here, that's the mechanical vibrator that oscillates this wave. And they're just like in figure 1, there's a node right in the center with a loop here and then a loop right here. Over here is a bunch of the materials that are over here. Some of the important ones to note are the sine wave frequency generator, the banana plugs, and this, which link up to create a frequency. This is the mass hanger that hangs on this string right here that is draped over the pulley, and that's just shown in this figure. So yeah, it's overall pretty easy to set up. For the procedure and safety, I kind of just went over all of that. This is a little more detailed explanation of everything. And really just one more important thing that I want to note is that I started at 100 grams and then I went up to 300 grams going in increments of 50. And talking about safety, the experiment was really safe. You just had to use your common sense with this. The string may snap and the mass may drop, however, they're not overly heavy, so it's not that big of a deal. It is very safe. This slide shows all the data. Right here is just the unprocessed from all the trials, and this is the process, being that it is the averages. So this graph right here. So how did I get the values in this graph? I used equation 7, which was previously shown how to derive, and I graphed the numerator and the denominator as seen right here, and it basically just produced this line with the slope equaling gravity. Over here, it does not look like it's gravity. However, right here, I kind of break down the units to show that it is meters per second squared, which is related to gravity. It is important to note the slope is linear, which means that the increasing of a mass on a string versus its frequency is proportional. And luckily, this experiment is within 5.2% of the accepted value of gravity. Now, also, the uncertainty ranges between 4.95% and 2.66%. All of these are the uncertainties, and that just has to do with the error bars and where it goes through. Also, the slope of the maximum, which is the red, and then the slope of the minimum sources of error is green. And those two values of gravity are right there. And it is important to note that it's 15.4% and 1.12% within the accepted value of gravity. So overall, very successful. So here's the conclusion. Key takeaways. Gravity was able to be determined. Increasing mass on a string is proportional to frequency. and comparable to other experiments with similar results because gravity was able to be found. So post-evaluations, what are some strengths? Well, first off, the experiment was successful. We used accurate scales, and we had a reliable mechanical vibrator. Some of the weaknesses were that it was hard to find the exact center of the node, especially at the lower mass points, and because the string was on a slight angle that could have affected it. Also, slight vibrations in the table/track may have impacted the investigation. So if I was to do an extension of this project, I would want to test strings with different linear mass densities and also change the thickness of the different strings because like a type rope, that is a very thick piece of string, whereas a guitar is more or less a little more thin. So I was wondering if something would affect different properties in those different variables. And for this experiment, if I was to repeat it exactly, I'll try to secure the track better, use a level string, and heavier masses at closer intervals would get rid of that problem where it was hard to find the exact center of the note. But here's my bibliography. And that's all, folks. Thank you for listening.